Okay, I want to run through a proof of the product rule. It's the same one that's in your book, but maybe with a little bit of a annotation here. Some of the mystery of it might be removed. So we're going to take the derivative, ddx, of a product, u times v. Now, the first thing we need to agree on is that u is actually a function of x, and that v is also a separate function of x. We're just kind of being lazy and writing it as u and v. But should we need to, and we will, we could write things like the u of 3 or the v of 7 or something like that. We can use our function notation this way, or the u of x plus h, or something like that. So u and v are not constants, they are actually functions. So when we take the derivative of u times v, we apply the definition, and we get the u of x plus h, v of x plus h, minus, I'll write it out in this notation, u of x, v of x, all over h, and of course I forgot we need to take the limit as h goes to 0. So somehow we've got to come up with our product rule for this, and it's a little Machiavellian. We actually know what the product rule is, but whoever came up with the following idea did not know yet, and I don't know who that is, what the product rule was. They played around with this for a while, and this might seem mysterious in your book, so that's why I wanted to put this in here. We have u of x plus h, v of x plus h. Someone somewhere said, hey, I can add or subtract a u of x plus h, v of x. I can do that if I want, but I can only do that if I also add a u of x plus h, v of x. So you see what we did there? We added and subtracted the same thing. So this net is 0. So we've added nothing. We've added 0. Don't forget our last term over here. Hopefully this is still in the screen, minus u of x, v of x. Oh, I should have done that back in purple. All over h. So we've added nothing. No big deal. I'm going to scooch over here, give myself a little more space. Now all we're going to do is rearrange that. So we're going to group these two things together. And when we group things together differently in addition, that's the associative property, in case you forgot. So if u of x, I'll write this quickly, u of x plus h, v of x plus h, minus u of x plus h, v of x, plus this part, u of x plus h, v of x, minus u of x, v of x. Our little parentheses in here because the associative property of addition says we can. Oh dear God, look at the mess we made. We're almost done though. All of a sudden out is going to pop the product rule that you know and probably love already. Okay, so notice we can factor. So, limit h goes 0, u x plus h, factor that out of hither and yon, and we're left with the v of x plus h minus the v of x, all over h, plus, notice I'm breaking this into two fractions as I go here, factor hither and yon the v of x out of this one, and we're left with the u of x plus h minus the u of x. This is really devilishly clever if you think about it. Someone had a wicked good idea. So now, hopefully, you recognize in there some sort of spidey senses tingling, saying this whole mess right here, that, as h goes to 0, is v prime. That's by definition the derivative of v. Oh, hold on. We're taking the limit of this whole mess. And this over here is u prime. So as h goes to 0, u plus x plus h, the h goes to 0, so this just becomes u of x. This whole thing here is v prime of x as h goes to 0. Again, over here, this is just v of x. There's no h in it at all. H going to 0 has no effect whatsoever on the v of x. And this whole thing, of course, if you look at it carefully, pause the video, look at it more carefully. Come ask if I'm glossing over that too quickly. That is u prime of x. And there you go. I didn't, on this other side here, beep, ditto, 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 ditto. I'll just rewrite the first line that we started with. So we have now proven using the definition of derivative that the ddx of u times v is equal to, now I'll just revert back to my lazier notation, u times v prime plus v times u prime. Happy, happy.